So we are working on solving Schrödinger equation. So the starting equation is given here. Okay. So generally Schrödinger equation is a 3D equation, but for simplicity we are going to start with a 1D. Okay, Schrödinger equation. Okay. So if you look at this one is a partial differential equation because wave function is dependent on time and space, and also it has a derivative with respect to x and time. So the way we kind of approach here is basically using separation of variable, and we were able to get two sets of ordinary differential equations now, right? So basically here, like from this separation of variable, we have one set of equation that depends on just time, and the second set of equation only deals with this part, and this one only depends on space. Okay, so this is the time dependent term, and then for this one the solution is simply this one right here. This is the solution for time dependent term, and then now this one is a space dependent term, the second order ordinary differential equation. And this is essentially, like what we are going to deal with quite often. Okay, so this one is actually called time independent Schrödinger equation. Okay, why is that? Because if we want to obtain the full solution, we are essentially using separation of variable. Look at this one. Okay, so once we obtain the solution, this is essentially our assumption here, right? So this is the solution for a full Schrödinger equation. So what we need to do is we have to find this phi, which is just dependent on time, and then we already obtained this solution, right? This solution is essentially this one. Okay, and then if we solve this time independent Schrödinger equation, we are going to get this psi of x, and then you are going to just kind of substitute that here. So then if we just multiply these two independent solutions, right, psi x and then phi of t, now we'll get a full solution, right, which depends on space and time. Okay, so here then now we are going to solve, and then if we solve this one, we are going to get this space dependent wave function. Okay, so again, just let me recap this one. Okay, so this psi t star, this one is probability density function as we discussed before. And again, the definition of this one is probability of finding matter at x. Okay. So this is a probability density function, and this is a probability of finding matter at given location here. And then let us kind of look at this one. Okay, if we integrate this psi t star and psi t and psi t star, what would it be, or what should it be? Since this psi t star, this term is the probability. Okay, in order for that to be meaningful, when we integrate this probability density function over the entire x space, what does it have to be? Typically, when you sum up all the probability, it has to be 1 in order to be meaningful. Does that make sense? Like a chance of something more than 100%. What does that mean? Right? So in the sense, here, when you sum them up, all the probability at any location, like if you sum them up, it has to be 1. Okay? So this is essentially what we call normalization requirement. Okay, for physically, like this to be meaningful, okay, probability density function. Okay, so again, in this case, since we are dealing with 1D, we are summing over X space, right? But if you are using, 3D domain, like if you are dealing with a 3D domain, this integration has to be over the entire volume. Okay, so this integration depends on the kind of dimension you are working with. Okay, so in the sense here, let me just write down for 3D cases, integration should be over volume. Okay, in the sense dx, dy, dz, right? But integrate. Maybe. Okay, integration, volume integration has to be. But again, since we are dealing with just 1D Schrödinger equation, we are dealing with just X space, we are just summing over X. Okay. So again, in this case, I just want to kind of re-emphasize that, like what we get here, okay, this represents just probability, okay. So, the consequence of this probability density function here is that Schrödinger equation results in probabilistic event. We'll see actually, like today, energy or momentum, all these physical parameters and locations are no longer deterministic. Okay, this one is kind of this one will be confusing, okay, but that is a direct consequence of solving Schrödinger equation. It's going to tell us just probability. So in the sense, even energy is going to be energy, momentum, and locations of finding matter. It's going to be just, the probabilistic event, okay, not deterministic. So what that means is that now this one will have average, okay, or what we call here is expectation and uncertainties. Okay, so in this case, this is essentially what we call standard deviation. Okay. So we are going to see, in a bit, but like when we actually solve this Schrödinger equation, it's going to tell us, for example, like a chance of finding this electron or matter at certain location will be only 5%. Okay, so like you cannot really tell that the electron or matter will be found at location, X, like 100%. For again, like for bulk scale object, right? I mean, if you are looking at like a bullets or like a tennis balls, like whatever, like the way we describe following Newton's law, we exactly know where the ball is going to be and then what the speed is going to be, right? But in quantum mechanics, those are no longer deterministic value. Okay, so like basically we have to talk about some probability, or essentially we are going to talk about average, okay, or expectation, and with uncertainties, okay, standard deviation. That is essentially what we are going to talk about. So then, how are we going to evaluate this average and uncertainty. So that is essentially what we are gonna talk about from now. So how are we gonna evaluate this expectation value, okay, or average or mean of any quantity? Okay, so this can be energy, this can be momentum, or this can be location. The way you calculate this expectation value is essentially, you integrate over the domain. But for that, you have to use this wave function, and then this omega and the psi t dx. Okay, so let me just kind of explain a little bit more about this equation. Okay, this omega bracket, this is essentially what we call expectation value. Okay, so when you see bracket like this, you will know that this should be expectation value or average. Okay, and then what is this omega then? This omega is the operator for specific quantity. Okay, so in the sense, whichever value or parameters that you are interested, this can be operator. For example, in this course, we are going to focus on position, okay, location, position operator, or we will look at momentum, mass times velocity, and also energy. Okay, this will be our focus. Okay. So in the sense, if you want to calculate expectation value of a position, so then you substitute this is omega with position operator, or if you want to calculate expectation value of momentum, you're going to substitute momentum operator with this omega. Okay? And then we are going to talk about that. And then the way you do here is that, now we should know, this wave function, okay? And then psi t star is complex conjugate of wave function, okay? And then this is wave function itself from, solving Schrödinger equation. And then this is the, the operator, okay? So the way you do is simply, sandwich the operator between this wave function, complex conjugate, and wave function, okay? And then integrate over the domain, okay? But in this case, since we are dealing with 1D again, we are gonna just kind of integrate over just X domain, okay? Okay, so then let us kind of now look into what these operators are, okay? So now let's start with the position operator. Okay, position operator is simply just X, okay? And in this case, obviously, this is a 1D case, okay? So what that means is that when we evaluate the average or expectation value of position, okay, that is essentially, we sandwich this operator between psi t star and psi t, and then you integrate over the whole domain of d over x, okay? And then we can also look at momentum operator, okay? momentum operator is given as, obviously we say P, and it is simply minus IH bar over IH bar dou over dou x. Okay, this is differential, and this one is again 1D case like we are talking about. So in the sense, if you want to evaluate expectation value of momentum, that is minus IH bar dou over dou x, and then you sandwich between psi t star and psi t, and then you integrate over the whole domain of x. Okay. The way you need to approach, for solving this x bracket or p bracket is you have to obtain you have to obtain psi t first, right? The wave function. How do you get wave function? You have to solve Schrödinger equation, right? Once you solve the Schrödinger equation, for a given potential, you can find what this psi t is. Then once you find that, you will have the solution for this and obviously this, and then you just put x here, and if you solve this equation, you are gonna get expectation value of a position. Or for momentum, you know what psi t is and psi t star is, and then now you kind of evaluate this one, right? If this psi t has x dependency, then when you do derivative, you do the derivative first, and then multiply by minus IH bar, and then you multiply by psi t star and evaluate integration. Okay. So it can be a lengthy process, but by doing that, you can evaluate expectation of position and momentum. Okay. So this one kind of seems odd, but you can actually derive this operator using the knowledge that we have, that is okay, because the momentum is simply mass times velocity, right? So in the sense, the expectation value of momentum can be evaluated by mass times d expectation value of a position over dt. Okay, that is velocity, right? And then we can also look at energy operator. Okay, energy operator is we write as Hamiltonian, and it's simply kinetic energy plus potential energy. Okay. So what that means is that it's simply p squared over 2m plus u, right? So here, I'm gonna make a note here. In classical mechanics, kinetic energy plus potential energy of energy conservative system is called Hamiltonian. Of the system. Okay. So for example, in classical mechanics, if kinetic energy plus potential energy is maintained throughout the process, right, there is an energy conservative system that is called Hamiltonian of the system. Okay. So we are going to deal with this Hamiltonian, that is simply kinetic energy plus potential energy. And then, the way we evaluate this energy is simply following this expression, okay? P squared over 2m plus u, that is, if we just modify the expression, we can simply write down as this one, right? 1 over 2m, p times p plus u, and then we substitute operator. Okay, for example here, minus momentum operator was given as minus IH bar dou over dou x, and then you just substitute here plus u. So, and then if you just calculate this one, right, I square becomes minus 1 and h bar square, then 2m here dou square over dou x square plus u. Okay, so now we have operator expression. Okay, Hamiltonian energy operator is given by that, and the momentum operator is here, and position operator is given here. Okay, so once we find wave function, now we can find out, expectation value of several physical parameters that you are interested. Okay.
Could you explain how that operator works? What are you taking the second derivative of, or what are you taking the first derivative of?
So here, the way we are gonna do is, so once, okay, let's just work on this momentum operator, okay, and then let us apply this one to this expectation value, right? So then, what you do here is, let's see. So here, momentum operator here, right? So we don't know exactly what this psi t is, right? But if we solve the Schrödinger equation, we are gonna get the solution, right? And then that solution is psi t, right? Let's say, just for simplicity, let's say that is sine x, let's say. Okay, if we solve the Schrödinger equation, we are gonna get the solution. But just for the simplicity, I'm gonna say, the solution is sine of x. Okay, then sine of x, or let's say just a little bit more complicated. Let's say I times sine x, Then psi t star is going to be minus I times sine x, right? And then now we have operator, but here it has dou over dou x. So you have to apply this derivative to wave function sine of x, right? So then when you apply that, it's gonna be essentially cosine of x, right? You take derivative, and then you have sine of x, and then you have some constant here, and then cosine x, sine x, cosine x, and then you evaluate this integration over the entire domain. So then once you do that, you are gonna get certain number, right? That number is going to be the expectation value of momentum. Did I get your question right, or?
So the operator, like the ddx, just applies to the wave function.
Exactly. Yes.
Okay.
So in the sense, basically this one is essentially applied to this next one. So if you look at this one now, for energy, right? We are gonna apply, well, for energy. It's going to come to the next page, so we are going to actually see this case. Okay. Okay. So, any other questions? Okay. If not, let us move on here. So, let me just kind of write down time independent Schrödinger equation again. Okay, it's given as d square psi dx square plus u psi equals e psi. I'm not sure if you recall. Do you remember how we set this e? Where was this e coming from? That is essentially, like when we were solving separation of variable here. Do you remember here? So when we were solving the separation of variable, we had to set constant, right? But here, I just kind of put e here, right? Just kind of, just for sake of just kind of putting a constant, okay? So this e was essentially kind of solved for this first step, and then that is how we got time independent Schrodinger equation. Okay, so this is a, like we don't know what this means, but this has to be a constant. Do you agree here? Does it make sense? That this has to be a constant. And then I'm gonna explain, like why we are using this E for the constant. Okay. So for example, in this case, we are gonna use Hamiltonian energy operator. Okay, h bar square over 2m dou square over dou x square plus u. This is energy operator. Okay. So with this one, look at this expression, minus h bar square over 2m dou square dou x square plus u. If you look at this left-hand side, we can actually apply as h psi equals e psi. Right? Do you see that? Because h psi, like basically if you apply this one, minus h bar square over 2m dou square over dou x square plus u psi is essentially minus h bar square 2m and d square psi x dx square plus u psi, right? Which is exactly same as the left hand side. Okay, so this one can be expressed in terms of Hamiltonian or energy operator. Does that make sense? Okay, so then let me just kind of write down here, and then the reason why we are converting from dou to d, that is because psi is only dependent on just x, right? Because this one is partial derivative, but anyways psi only depends on x, so it's essentially ordinary derivative. Okay, so here what we are gonna do now, evaluate here the Hamiltonian, okay, the energy expectation value of the energy, or the way we can simply say is energy, right? We are gonna find out expectation value of energy that is essentially evaluated by negative infinity to infinity and psi t star h psi t dx, because energy operator is simply Hamiltonian, right? Like as we discussed here, energy operator is Hamiltonian. Okay, so then let us now look into this one. Okay, psi t is given as psi of x and phi of t, right? If we express this wave function, this is a full solution, right? It has to be, just kind of following separation of variable argument. We have to have x dependence and time dependence function. And then if we substitute here, what we get is a negative infinity to infinity and psi star and then phi star and then h and then psi and phi of dx. Okay, right? Because psi t is a psi phi, and then here we are taking complex conjugate. Okay, and then here, remember or recall what was a phi. That one was e to the minus I e t over h bar. Okay, that one was the solution by solving, time or first order ODE from the separation of variable, right? This is the solution coming from this one. Okay, here, first set of ODE, right? So I'm just using this one, phi, and then in this case, e to the minus I e t over h bar, and then phi complex conjugate is simply I E T over H bar. Right? We are just kind of converting a sign for a complex number. So then look at this one. Okay, so now phi, we have a phi here, and then we have a phi star here, right? Phi star and phi. If we put it together, that is e to the minus I e t over h bar times e to the I e t over h bar. That is essentially e to the 0, and then that is 1. Okay? So in this sense, now phi and the phi star basically becomes 1, right? So this makes our life easier, and what that means is that now from here to here we have only negative infinity to infinity psi star h psi dx. Okay? And then let's use this one. Okay, h psi equals e psi, right? This one, h psi equals e psi. So what that means is that from here what we have is negative infinity to infinity psi star e psi dx. Okay, we are just changing or substituting this h psi with e psi. Okay. By the way, if you look at this e, what was this one? Do you remember? This one was constant, right? Constant. So what that means is that this one can come out of it, right? Because it's constant. So what that means is that now this one can be expressed as e integration negative infinity to infinity psi star psi dx. Okay? And then if you look at this one, what is this? This is a probability density function, right? Probability density function integration over the whole domain of x. And then what does this have to be? This has to be 1 because of normalization, right? So in the sense, this one now becomes 1 because of a normalization condition. Because this is a probability density function, and then when we are integrating over the whole domain of x, or in other words, if we are summing up all the possibility or probability in x space, it has to be 1. Okay, so this one turns out that it is e here. Okay, so what is that? What we are evaluating here is expectation value of energy, right? Expectation value of energy. And it turns out, okay, so if I kind of just reiterate here, when we evaluate expectation value of energy, it turns out it is that constant, right? That constant. So this is why, it could be like any value, right? For example, here, we could have written this as alpha or beta, right? Alpha or beta, it can be just any constant, but it turns out this constant has physical meaning, in a sense that, why? Because if we evaluate expectation value of energy, it turns out it is that constant, right? So that is why, we are not writing like alpha or beta for that constant, we are just simply writing as E here, because this E is the expectation value of energy, okay, of this system, okay? So in the sense, again, constant E we set for the separation of variable it turns out expectation value of Hamiltonian. Okay? So that is why, like when you look at the time independent Schrödinger equation, we have this E here, okay, the constant. Okay, so then now we looked at, the average value, right? But when we talk about the probability, probability distribution, the average alone does not give you a full picture, right? Because, like an average, it's just telling you where the kind of mean value is, right? But when you look at distribution, another important parameter is uncertainty, how the spread values are, right? So that is essentially standard deviation, okay? So we have to actually look at also standard deviation for any distribution. So because standard deviation tells you how spread out the values are, around the mean, right? So for example, if you have a large standard deviation, there are many values are spread all over, right? But if you have a very narrow standard deviation, what does it mean? It's basically like all the values are centered around the mean value, right? So they can kind of give you some pictures of distribution, okay? So how do we get standard deviation? By definition, it is square root of the average of the squared differences from the mean. Okay, so for this one, let me just kind of let's just discuss a simple example. I know this one is so obvious, but like I want to use this example for another one. So just kind of bear with me. We have, let's say, the 5 data points, and then we are trying to find the standard deviation. Okay, so obviously we know the average or mean is essentially 3, right? Because the way you calculate in this case is that the first way, when you evaluate the average, probably this is what most people do when you sum them up and then divide by the number of elements, right? Or second way is essentially, you pick the one element, and then what is the chance of picking this element out of all the samples? That is essentially, it has 20% chance, 1/5, right? And then you keep doing that, okay? You pick one element, what is the chance of picking that? And then you kind of keep adding it. And obviously, it's going to be the same, right? But anyways, there are 2 ways. But this is actually something that we are going to use, okay, in later kind of section, like for developing the mean expression, okay? So now we have to find the difference, right? Because here standard deviation is square root of the average of the square difference from the mean. Let me just kind of find out this difference from the mean. So what it means is that now difference of mean is 1 minus 3, which is minus 2. Here 2 minus 3, minus 1, 3 minus 3, 0, 4 minus 3, 1, 5 minus 3, 2. Okay, so this is the difference from the mean. And then when we square, it's going to be 4 41014, and then now standard deviation is now, we evaluate the square difference from the mean. We have to take average of that, and then we have to take a square root. Okay, so what that means is that now standard deviation will be evaluated by 4. Now we are going to sum them up here. 41014, 0 plus 1 plus 4, and then divide by 5, and then if you take a square root here, and this will be essentially square root 2. Okay, so that is how you can obtain standard deviation, okay, over these values, right? So this value essentially tells us how spread the values are, okay? And for example, like instead of 1, 2, 3, 4, 5, if we describe as like a, minus 1, 0, 2, like a 6, 7, the now values are more spread it out, and if you evaluate standard deviation, it's going to be greater than square root 2. Okay, so with this one, let me just kind of formulate the equation for standard deviation. Okay, so the way we are going to approach here, let me just kind of use the kind of notation. Okay, now bracket. So when I show the bracket like this indicates the mean value, okay, the expectation value. So that is essentially mean and expectation. Okay, and then now, like in order to formulate this standard deviation, we have to find this difference from the mean. Okay, the way we are gonna do here is, this delta J is essentially indicates difference from mean. The way we can express is this J minus J bracket. Okay, this J indicates the value itself, and then minus the mean value or average value, right? So that is essentially this delta J, the difference from the mean, or this part, 1 minus 3, 2 minus 3, 3 minus 3, right? Because here J is constant. Okay, when you are given the distribution of the values, data, this J is going to have one single number, right? It's not going to change for the given set of the data. Okay, so this is a mean value, but this J is the element value itself. Okay, so this is a difference from mean. And then now if we evaluate this sigma square, okay, this is a sigma. Oh, I didn't write down here what the sigma is. There's standard deviation, okay, or sigma here. Get sigma square, that is the square of standard deviation, is given as J minus J bracket and square average. Okay, why is that? Because let me just kind of copy this one. Okay, standard deviation, the definition is here. Okay, this is a standard deviation. So square root of the average of the square difference from the mean, but don't worry about this square root because we have this square here. Okay, so in the sense we are going to just focus on average of the square difference from the mean. So this is the, again, what is that? This part is difference from mean, and then we are squaring it. So we take care of this part, and then we put the bracket. What does it mean? We are considering the average, right? So this is essentially, conceptually same as this part, right? Or like more precisely, if I just express in terms of standard deviation, that is square root here, J minus J bracket and square bracket, right? So now if you, this is a standard deviation, is a square root, this part, and the average here, and then square difference from the mean is essentially this part. Okay. So just by following definition, we can develop the equation for standard deviation, and also this can be expressed in a slight different way, which is j square bracket minus j bracket square. Okay. So conceptually, what does this mean? J bracket is simply average, right? Average, and the average squared. And then this one is actually has a very different meaning. What that means is that element squared, you are taking average of that. Okay? So when you evaluate this, and then when you evaluate that, and then when you take a kind of subtraction, and then that is essentially standard deviation square. And then we can actually go through the proof here. Okay? So let me kind of show you why this one has the same expression as this one. Okay, same value. So here, proof. Let us look at this one first. Okay, so here this is the delta J. For example, delta J square. Okay. So where did it come from? This is simply coming from here, because here j minus j bracket is simply what? Delta j, right? The difference. So if you just substitute here, delta j written here, and then we have square, and then average. Okay. So how do we evaluate average? Okay. The way you take average or obtain the average value is simply summation of this delta j square value and then the probability of picking j. Okay, so we can actually evaluate average following this one. This is essentially the same concept as this part, right? For example, here, when we evaluate average here, you pick that element, right? And then you kind of consider the chance of picking that element, and then you just sum them up for all those elements, right? So if we follow this concept, you can actually express this way for obtaining average. Does that make sense? Yeah? So for example, again, like when you are evaluating, we have to evaluate the average here, right? So for this average value calculation, what we are doing is simply following the second way. So for example, we pick that element and then consider the chance of picking that element. In this case, equally kind of a possibility, right? So there's 1/5. And then you consider the second element, which is 2, and third element 3, fourth element 4, 5, right? And then you sum up for all those elements. And then in this case, is exactly what we are doing, okay? So you are summing up for all possible data points, and then you evaluate this delta j square. This is the element value itself, and then what is the chance of picking j, you consider that, and then you sum them up, okay? So then you will get the average value, okay? So then we can actually keep carrying on, but for the given time, we can actually stop here, and we'll continue tomorrow.